Okay. 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 Today, let's move on. Let's continue to talk about that motion sensor, right? Accelerometer. We discussed the last time. You gave presentation, right? So today, we are going to talk about hardware system design and software programming accessing the device, right? So we are talking about that LIS2DH accelerometer or motion sensor. That is from ST Microelectronics. You know, check out that company. This one. This logo, right? ST. That ST Microelectronics. That is, you know, very famous company actually. ST Microelectronics. Okay, they are providing, you know, these, you know, devices. Okay, check out that. And you know, LIS2DH, that is located at the center of this board, right? This small, this tiny device that is called LIS2DH, right? So, and you know, so it is, you know, this board manufacturer created this PCB and mounted that LIS2DH and provide that connection, an I2C connection. As you presented, that device is providing two kinds of protocols. Right? First one is SPI, and the other is I2C. But you know, this board is already fixed to use I2C protocol to access registers. Inside that tiny chip. So we don't have any choice. So we have to use I2C, you know, communication to access that, you know, that device. And this device is providing very interesting characteristic, right? Functions. You know, it is detecting motion. What do you mean by motion? It is detecting direction and how fast you are moving. And also, you know, as a bonus, it has temperature sensor, right? So that can be used. Probably that, you know, that device can be used in what kind of applications? Think about that. What kind of applications do you want to use that, you know, accelerometer? You know, smartphone has, right? Our smartphone has accelerometer. Okay. So your portrait and landscape, you change your smartphone, then, you know, the screen got changed from portrait to landscape automatically. It, you know, detect your motion. And drone, right? Jinok is working on that drone, right? A drone, you know, inside drone, you have that accelerometer. And self-driving car also. There are many different applications you can use, right? Okay, and then what else we have to talk? Okay, and then you know, the using that accelerometer is pretty simple. It is, you know, one kind of I/O device. Right? That tiny device, LIS2DH. Okay, that is one kind of I/O device. And I/O device, every I/O device is providing three kinds of registers, right? So first one is configuration registers. Config. Before you use the device, you have to set configuration, right? You have to set operating condition, okay? Then data register. Data register. So X, Y, Z, and temperature. So those are, you know, data register, okay? And then status register. Some event happens. For example, temperature is too high. Ambient temperature is too high. You can generate interrupt, right? Even though we are not using interrupt, that is not connected. That interrupt pin is not connected to outside world. Okay. Anyway, status register, right? So using that I2C connection, using this I2C protocol, your job is to touch, you know, configuration register, read from data register, and check status register. That's what you have to do. Right? and connect this device to your, JET board. We have JET board, right? And inside this JET board, you are supposed to have I2C controller. Okay, so that is also I/O device. One I/O device. Okay, we have ARM CPU. Okay, then this I2C controller is also providing some registers. So using those registers, you are generating, not you are, right? This hardware is generating, I2C transaction, this actual transaction to access, those registers. So let's talk about hardware side first. Okay, so let's back up a little bit. Because we are going to use I2C, protocol. Let's talk some more about the protocol and connection and protocol. Okay, so that is the picture. I2C is very low cost and very inexpensive communication protocol because we are using only 2 wires, clock, SCL clock, and data. Clock and data, only one, okay, 2 wires, right? Clock and data. So many different I2C devices can be connected to these 2 wires. So you can send the data. Device 1 can access registers in device 2. Okay. Device 1 can access register in device 3. So master, slave. Okay. Device 1 can be master, device 2 can be slave, or vice versa, right? Device 2 can be master, device 1 can be slave. Okay, so very, very interesting and simple and inexpensive protocol. It is very widely used in industry, actually. So as the name implies, what it stand for? What does it stand for? I2C. Inter IC, right? Let me show you. I2C protocol. Check out the acronym, right? Integrated circuit. Inter, right? So that is IC, and you have another, integrated circuit, right? So between these 2, integrated circuit, you want to do communication, right? So this device, this IC, and some IC in JET, right? So IC, integrated circuit, physical, IC, not, not SoC, right? So, not SoC, right? System on chip. SoC, in case of SoC, many different modules, right? Including ARM, CPU, not ARM, CPU, memory, and many different I/O devices, right? Are integrated inside a single chip. That is chip, right? Chip. And one is probably I2C controller. Okay? And then another SoC, right? System on chip, and another SoC. Okay? They can be connected through that two wires, right? SCL and SDA. Same thing. You have I2C capable system on chip. You have controller, then connected like this. So these 2 guys can talk to each other. So that is big picture. And each I2C device has a unique address. Like this, right? LIS2DH case. It has 1.8. Address is 1.8 in hex. Right? So by generating transaction, so JET, right? This master device, for example. Master device is generating transaction targeting 1.8. Okay, then this guy can respond. Okay, so not, the other slave devices are not responding, right? Only that device. And probably you are not that comfortable with this, this register, right? Registers, pool of registers, right? Because you are not EE major, right? Electric circuit, electrical engineering major, right? Let me let me talk a little bit. You have GPIO, for example. Let me give you, some related example of that, pool of register. So that is a zinc, based zinc, based zinc. Okay. So GPIO, you configure this GPIO as an input device. So you want to connect switch, for example, right? You want to connect. So 8-bit, 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8-bit. Then this bit is connected to, for example, switch like this. Okay, so you can close the switch and open the switch, or you can turn on, turn off, right? Press or release, right? So what if your GPIO is configured as an input device? What if you don't connect anything, for example, like this? What if you don't connect anything here? Then what would we are talking about, digital. We are living in digital world, right? So we are expecting 0 or 1, high state or low state. High state is 1, logic level 1, or depending on operating voltage, 3.3 volt, 5 volt, whatever it is. Anyway, logic level 1. Low state is logic, 0 ground, 0 volt. So again, if you don't connect anything to this input, then what is the input state? What do you think? What do you think? If you don't connect anything, just air, right? Air, nothing is connected. Open, right? Is open. Then is it high or low or what?
그게 아무 신호나 랜덤하게 그냥 읽는 걸로 알고 있습니다. 하인지
Okay.
로우인지.
Okay. Guyon, what do you think?
이렇게 그냥
이렇게.
예, 그때 다르죠.
Okay, yes, yes. This one is called floating, right? So it is floating. Float, floating. So nothing is connected. You cannot determine the state, right? So probably in between high and low. So if the operating voltage is 5 volt, let's say 5 volt, then you never know, right? Probably 2.5 or 3 volt, right? The floating state. You don't know, right? You cannot determine, right? So then there is a problem, right? There is a problem. We are talking about digital. We want to keep this input in known state, high or low, because we are living in digital world, right? 0 or 1, right? So if you connect switch, for example, or you can connect like this. Going back to ground, that is ground, 0 volt, right? So you close the switch and open the switch, right? Press or release, right? Then if you press the button, if you press the switch, then it is very easy, right? 0 volt, right? 0 volt is connected to that input. So that is for sure, zero state. What if you open? What if you open the switch like this? What if you release the switch? Don't press, release the switch, then what is the state? It is like a floating state, right? Nothing is connected. Floating state, nothing is connected, right? So you have to do something. So in this case, you have to use, typically we use pull up resistor, 5 volt, 10 kilo ohm, something like this. Then if you open the switch, if you release the switch, if you release the button, then this guy is connected. This guy is connected to 5 volt. But it is very tricky because you are not EE major, electrical engineering major. Then this 5 volt, this node is equivalent to 5 volt or 4 point something volt. What is that? How do you determine this voltage? Okay, so some intuitive way to interpret this voltage. We studied the Ohm's law, right? V is equal to IR. Right? So you have, say you have 2 resistors connected. Let's say 1 ohm, 4 ohm. And let's say you have 5 volt. 5 voltage, battery, 5 volt, okay, plus minus, connected. Then current is flowing, right? Current is flowing. So 1, 4, so 5 ohm, R is 5, and V is 5. So I is supposed to be 1 amp, right? So voltage applied to this, resistor. Voltage applied to this resistor is 1 volt. Okay, 1 multiplied by 1. So in voltage applied to this resistor is 4 volt. Okay, so that node is 4 volt. Now 0 volt, then 4 volt higher than this one. Okay, and this one is 5 volt. So 5, right? 5 volt. So voltage divider, right? If you connect these 2 resistors in series, right? Not parallel like this. In series, right? Series, then voltage is divided. Source voltage 1 volt, 4 volt. So 5 volt. 5 volt. Okay, then to interpret the circuit, okay? So this is 10 kilo ohm. Okay, this is 10 kilo ohm. Okay, but 10 kilo ohm. And don't think about, this input. Don't think about input. And you open the circuit, right? And what is the resistor R? Resistor of that, this one. Open, right? Close to infinity. This one is close to infinity ohm. Open, right? Resistor air, right? Resistor is infinity. Then, infinity 10 kilo ohm. So it is nothing. This one is nothing compared to this infinity. You can just ignore that part. So the voltage of this node is very close to 5 volt. You can just ignore this connected. No resistor. That is some intuitive way to interpret this electric circuit. Think about the extreme case. Okay, for easy interpretation. Okay, so you have infinity, then very small resistor. So infinity, very small. Just ignore this, right? Infinity. So 5 volt, whole 5 volt is applied to that resistor. So equivalent circuit. This one is equivalent air, right? Air is almost infinity resistor. Current is not flowing between air, right? Current is not flowing. So that is called pull-up resistor. This one is called pull up register. This one, that pull up register. So by using this pull up register, you can, this pin, this input, this wire can be either in high state if you open, okay, or low state if you close. Okay. So that is what you have to connect on board actually. Okay. So let's check out our hardware system. This one. So that is hardware system. I'm providing to you. Actually, I spent too much time. Actually, I spent almost 1 week to figure out that I2C communication and cook up this working, demo during winter vacation. Don't sleep. Right? I spent too much time on this. So here, if you here, right? Last time I told you in Korean, I explained to you this processing system. Double click this. I enabled this one, I2C. We have two I2C controllers inside Sync device. Okay? Inside that PS section. Okay? Inside light gray PS. Okay? And dark gray PL. So inside this PS, you have two I2C controller. Okay, one of them is enabled. First one is enabled. Okay, enabling it very simple. Enabling how to enable very simple. Just check the box. Check this box. Okay, then you will see that output appear. That I2C, that output appear. Then make it external I2C. Okay, then. You have to map, you have to assign specific pin, Sync pin to that I2C. That is defined in constraint file. Source, constraint, LED, Xilinx, some constraint file. So here, look at this. This one. Clock and data. Clock is assigned to W7. Clock is connected to W7 pin, and data is connected to V7 pin. And one thing you have to be careful is this one, pull up. Pull up. Okay, pull up. So Xilinx is providing pull up capability. So implement that hardware design, right? You do synthesis and implementation, check out this. I already did that. I don't have to go through because it takes time. Check out that pin after, check out that W7 and V7 pins after implementation. Okay, this is the one. And IO port. So again, W, right? W and 7. So that pin, right? That is clock. Right? Check out this. Clock, right? SCL and data. Then pull up type, pull type. This pull up, pull down, keep or none, something like that. Okay, that's the one. So you have to be careful about that pull up, okay, to make it work. That is hardware system design. Okay. And let's talk about, a little bit about the packet format or transaction format. Okay. Okay, so before that, let me show you the design again. Okay. If you want, probably you can add. Okay, if you don't like I2C controller inside the PS, you can add intellectual property hardware module I2C. Okay, I2C bus controller. You can add if you want. Install. Okay. Transmitter I2S does not provide. Probably you can, if you install I2C controller IP, then you can instantiate that IP into this design, like GPIO, right? We instantiated GPIO device here. Okay, like that you can instantiate I2C master device. Okay, custom. The reason why I want to show you is because of the data sheet. But you don't have to. So here, check out Zinc technical reference manual. So PS, it is talking about PS, right? Devices from CPU to many different IO devices. Okay, inside the PS. So check out this I2C, chapter 20. Okay, that is the one we are going to use, right? This I2C controller. Okay, and it is very short. I think documentation, page 610 to 625, only 15 pages, right? And then check out this. It's talking about I2C 16-byte FIFO master mode. We want to use I2C controller in master mode, right? Zinc is initiating transaction. Okay, and motion sensor is responding to the transaction, right? So master mode only. So you don't have to read the slave mode operation. Okay? Master mode operation only. So scroll it down. So I2C device inside the Zinc then is providing some registers, right? Configuration register, data register, status register, right? Then clock connection and data connection, SCL and SDA, that is connected to some pins, output pins. In our case, W7, remember? W7, some V7, I think, that is connected. So scroll down. So what you have to read is master mode operation. Our I2C, that device, is operating in master mode. It is initiating. So this one. So Zinc using these two, SCL, SDA. We connected motion sensor to the H. Okay, so motion sensor. So I2C controller. C controller. That is operating in master mode. This is a master, and that guy is slave. So master mode only. The initiation transaction responding, right? So what you have to read is master mode operation. So look at this, 20 to 2. slave monitor mode, you don't have to read, right? And then multi-master, we are not that interested in multi-master operation. We have only two devices, master and slave, right? So very simple. Only 2 pages, right? Master mode operation. Write operation, you want to write to register, right? And then you want to read from this device. Read and write, right? Very simple. Okay, that is talking about, detailed operation, and then some detail about clock frequency. What frequency do you want to use? I2C frequency. So using clock divider. Using clock divider inside this hardware module. This one is clock divider. Clock divider. So you have an incoming clock, right? ICLK, for example, incoming clock. Clock is running at pretty fast, for example. So according to the table, okay. So let's say, for simplicity, 100 megahertz input clock, ICLK. Then internally you want to generate some output clock, OCLK, by using that clock divider. So if you divide that clock by 2, this one, I clock divided by 2, then 50 megahertz, for example. So how do you do division? Very simple. Every rising edge, you invert the signal, right? So here, for example, we don't know the first state, but here, let's assume 0. Then here you invert. At this time you invert, then invert. Okay, rising edge, you are inverting. Rising edge, you are inverting. Next rising edge, you are inverting, and so on. Then you do, clock division operation. Simple, right? So, by writing some value to clock divider, you can cook up any clock you want. Okay, so formula is this. Okay. Formula divisor A, divisor B, then output clock. Right? So using this one, 1 and 16, 2 and 16, sorry, 2 and 16. Okay, plug that number into that formula. Then you can cook up that to this. See. So here, input is this one, 111 megahertz. So 0, 0, 0. If you convert that into kilohertz, right? Mega and kilo. So 111 divided by what? Where's that division? Okay, division. Then 2, 3. 2 plus 1, 3 divided by what? 16 plus 1. 16 plus 1. So 17. 1, 7. Something is wrong. What happened? Did I do something wrong? Anyway, okay. Anyway, I don't know. Okay, you can do some math. Probably I have to. Okay, I have to use this one. This formula. Probably. Okay. Anyway, by programming some value into clock divisor, you can cook up any frequency. But I2C is typically operating at within from this 100 kilohertz to 400 kilohertz. That is typical clock frequency. Okay, so using that divider, create that output clock. So SCL will be operating based on that clock. Right? And detailed information about registers. registers I2C controller is providing. So you can scroll it down. Register detail. Okay, that's the detail. Where is I2C? Here. I2C controller registers. Okay. Only few registers, not many, right? Look at this. So that is talking about this. Don't be confused. There are some registers in your motion sensor, and registers in I2C controller. Right? So I'm talking about that table is talking about registers in I2C controller. Using that I2C controller, using that registers, not divider, right? Using the registers, you can generate transactions. Okay, read transaction and write transaction to read from this device and write to this device. Okay, don't be confused. A little bit confusing, right? At first, some registers. Okay. So by reading this name, right? Reading this register name, it is not that hard, right? You have a control register CR. Before you use I2C controller, set up operating condition. So clock, operating clock frequency, for example, 100 kilohertz, 400 kilohertz. How fast you want to do communication, right? Using CR. Check out CR, right? Look at this, divisor, right? Divisor A, divisor B, and so on. So you can set operating condition using configuration register, then address register and data register. Address register, what do you mean by that? You want to program. So here you have address register, right? Address, what address? So that address. So in our case, this one, 0x18. Okay? That is ID, unique ID for that motion sensor. So you program 0x18 like this. Okay? Very simple, right? And data register. Which data? What data do you want to transfer to that motion sensor? So check out that registers, and so what you have to know is all the registers, right? From software point of view, what you have to do is touch those registers. That's it. That's what you have to do, right? Then I2C controller. By looking at only registers, you don't know. You don't have any clue, right? So that is why you have to read that explanation how that is operating, right? So that is the one to use that I2C controller. Okay. Then let's check out packet format, transaction format, I2C. We are not talking about detailed transaction, very simple transaction, right? So I2C protocol, if you dig into the detail, then I2C is providing some detailed protocol, but we are going to stick to very basic one, not in depth, very detailed. Some multi-byte transfer. We are not going to talk about that. One byte transfer, for example. So transaction. If you read the registers in I2C, you can generate that actual transaction. Actual transaction running on these two wires, SCL, SDA. Okay. So first, transaction start with start condition. Start condition can be start condition is this. Data line supposed to goes down while clock is high. Then there is a start condition. So slave is checking that start condition. Then condition is met. Then that guy is preparing to take to take address and data. Simple, right? And stop condition, opposite. The data line goes up while SCL is high, clock is high. That is stop condition. So in between these two, you are sending this controller. It's sending bit by bit, sending address and data, right? Address, right? So which device you are targeting this address? On it, for example. Okay. And what operation do you want to do? Next bit, read operation or write operation? You want to read from that device or write to this device? Okay. And this white, okay, look at this legend. This sky blue is initiated by master. Sky blue initiated by master, and white is initiated by slave. Slave, right? Look at it. So master is sending address and operation, read operation, write operation. Then slave is responding. Slave acknowledgement. Okay, I take your request. Okay, I can take. I acknowledge. So it is like handshaking. Handshaking, right? You are sending something, then okay, it is acknowledging, right? Then 8-bit data from master. Then acknowledgement, or no acknowledgement if this guy cannot take it. Right? That is basic format. Okay, some details here. This one. Kiwon, can you please read?
Data validity. The data on the SDA line must be stable during the high period of clock. The high or low state of the data line can only change when the clock signal on the SCL line is low. One clock pulse is generated for each data bit transferred.
Okay, you don't have to worry too much about the detail, but for your reference, data, when you send bit by bit, not you, right? This controller generating transaction, send data bit by bit. Data supposed to be stable. This data SDA, right? Data supposed to be stable during this high clock period. So that is a requirement. But again, you don't have to worry about that, right? This controller is generating right transaction for you. If you with the registers, don't worry too much, right? There's the one. So here, start condition, stop condition. You are sending, controller is sending address information here, MSB first, then data. Okay. Okay, then this is the connection you have to make to access this motion sensor. And we are using red is 3.3 volt, right? Green, black, 0 volt. This green, is it green? Anyway, green is data and blue, clock. Okay. 1 second. One thing you have to be, one thing probably confusing is by looking at this protocol. That's what I was struggling at the beginning of figuring out this, the hardware and software detail. So one thing very confusing is this. Take a look at this. This one, according to I2C protocol, you are sending what? Address and next data. This master sending address 18 and data, right? But one thing is not clear. What is not clear? So you have motion sensor, let's say LIS2DH. It has many different registers, right? Many different registers. Right? So temperature register, X register, Y register, G, many registers, right? But according to I2C transaction, you are sending address 0x18, right? And data. So 0x18 is what? So this device ID 0x18, device ID. You are not talking about which register you want to access, right? And data. So what do you mean by that? You are talking about, okay, the transaction is for that device 18, according to that 7-bit, and data. Then what data? You haven't selected the register. Which register you want to access? That is confusing part, right? Isn't it? That's what I was very struggling at the beginning of preparing this reference design, right? The secret is this. If you look at this data sheet, LIS2DH, let me show you read transaction. Okay, read transaction. Probably that is more intuitive, probably. So transfer, when master is reading, this master, that guy is reading, for example, that guy is reading, okay, I want to read from temperature sensor data. I want to read from this register. Then what do you have to do? You have to generate those transactions. That is what this data sheet says. Okay, so look at this. What is that? The acronym. There are acronyms. ST, start, right? Start condition, right? So obvious. Start condition. Then S says the slave address. This one, 0x18, right? Slave address, and with write operation. Strange, right? Receiving, right? Reading. You are reading, but you have to write. Write what, right? So, but write transaction and slave. Slave is responding. Slave, this motion sensor is responding. Okay, I'm acknowledging. Okay, this address and write transfer and sub. Sub is what? Sub is 8-bit sub register number. Okay. So there are many registers. Which one do you want to access? Okay. That should be transferred. Sub. Okay. Then slave will respond. So a slave acknowledge. Then there is some, I2C protocol. SR means repeated start. That is part of I2C protocol. Okay, repeated start. Then again, slave address, slave 18. But now read transaction. Okay, so what you have to do is, let's say temperature sensor, the location is 0x0D, register number. Okay, so first, what you have to send here, solve, okay, this green is 0x, this one, 0x0D, 0D. Okay, so here again 18, then 0D. Okay, so motion sensor. Okay, I want to access motion sensor. Then I want to access temperature register. So write transaction means so you are writing. You're writing you're writing, okay, somewhere, right? Inside this device, not this register. Inside somewhere, there's a buffer, I think. Some buffer to store register number 0x0d. Okay. Then next one, source address. Source address again 18. Okay, I'm targeting that guy. But now read transaction. Read transaction. I want to read from the register. Okay. So buffered that one. Read from that sub green. You read from the register. So slave will be respond. Slave will respond with the data. So it sounds pretty complicated, right? So let me show you. Software. Okay. So you don't have to worry too much about that. I figured out everything. So providing. Let me show you side by side probably. So from here, launch, software development environment, turn on. Okay. So here, workspace, this one, okay. Close hardware design. So I made connection. Let me show you the connection first. So here, full screen, right? So this one is for monitoring. This logic analyzer is for monitoring the two wires, SCL and SDA. Look at this here. This one is connected. This one is connected to this breadboard. So these 5 dots, vertical 5 dots are connected. Okay, that means the wires are in same color. You cannot differentiate. For some reason, this video hard to distinguish colors, right? So here, a green. These 3 green wires are connected together. Okay, and here 3 blue wires. Okay, 3 blue wires on the right side that is connected together. So the first, blue is coming from here, from this pin, and green also coming from this pin. Okay, then motion sensor is here. Okay, so that okay. So again, this one, these 2 wires are connected to motion sensor. Okay, motion sensor, and then also these 2 wires are connected to logic analyzer. I want to check out the waveform. Okay. Okay, there is one. Take a look at this. So example code. So C code, not assembly. Okay, C code. Okay, good news, right? C code. Then actually, I think I Google search some reference code for accessing the motion sensor, and I found the reference code, but I forgot where I found it. From where? Anyway, this is the one. So here you are setting up. You are setting up. Okay. You set up I2C clock. Okay. That clock, okay, the SCL clock. Okay, you are touching registers, control register in this I2C controller to set up operating condition. Okay. So clock, then I'm reading, look at this, LIS2DH API, right? It's API. You are passing base address of this I2C controller. Okay? Base address of that controller, because you want to touch, some registers. You want to touch registers. Then don't be confused here. Who am I register, right? You read the motion sensor documentation. One of them is, who. One of the register is who am I register, right? You want to read, for example, that register. Okay. Then it is, you are passing pointer, then, ID will contain. After you return from this function, that ID, who am I value will be contained in this register, in this value, in this variable. Okay, so we are just printing out. Okay, so good news is LIS2DH read API, then that is defined. Scroll it down here. That function LIS2DH read. Okay, and if you check out that code, this function, look at this API. Master send API. Right? Here you are sending address, which there is, look at this, 18, right? Motion sensor address. Okay. Then TX buffer, you are sending master send, right? Writing TX buffer. You are writing the data in TX buffer. So register offset. Which register you want to access? Okay. So you specify, you are passing a register number as an argument, right? That offset is this one. That is contained TX buffer. Just one size, one byte, I think. Cha, right? U8. So 1 byte data type. So using this API, you can send it. To figure out detail, you can press F3. Then you can check out this source code, master send port. Then here, flag right. Okay. Just follow the code. Then if you want to know about this API, then press F3. So here, writing something to that register. Okay, so you can do this. But the good thing is, it looks very confusing and complicating, but the good thing is you are supposed to use just two functions. Is write and read. Read and write, that function, to access motion sensor. That's good news, right? Use just the API. Okay. So read, write. Okay, some control register. I'm configuring control register in motion sensor with what? This is the data. You want to write to control register in this motion sensor. Okay. And then here, as an example, I'm checking what? Look at this for loop. This for loop is checking temperature, ambient temperature, high and low value. Okay, and printing out that high and low to the screen. Okay, we are going to talk about serial communication. What do you mean by printf statement? How do you print? There is no monitor on JetBoard, right? No monitor connected to JetBoard. How can you see this message? Through UART, serial communication. We will talk about that after, probably next week. Okay, but for now, let's just use that I2C communication, so UART communication. Okay. Okay, so let me just execute that code here. Download it. to the board. Debug. Okay, this is the one. Then debug. Okay, before press F8. F8 means what? F8 means you keep running this code to the end, right? Before you do that, let me set up a UART communication, serial communication. You can either use this one. So this Vitis is providing a serial communication capability. But let me use different tool, okay, called Teratom, different program to take input from, take message to take input from a JetBot, okay, and run it. Okay, let me press F8 and it is temperature is 8, 9, something like that, right? And it will print out 100, right? So look at this for loop, 0 to 100 messages. Okay, so if I blow hot air from my mouse, okay, do this. Goes up, right? Okay, goes up. Okay, then let me use the ice pack. Because my office is pretty hot, let me use ice pack. I have to be careful, okay? Don't be careful, right? Sometimes the device will be, I don't know. Okay, supposed to go down, right? 7, right? The temperature goes down, right? Because it is on top of that ice pack. Okay? Temperature goes down. If you blow hot air from your mouse, then it goes up. Okay? It's working, right? And but by looking at this message, but you are suspicious. Really I2C packet transaction is really happening, or I'm cheating you. Okay, so you are suspicious, right? That is why we want to use logic analyzer, right? Let me change the loop to 1000. Okay, I don't want to compile it. Run it again and again. Okay, so let me. Then let's use logic analyzer to check out the actual transaction going on, running on these 2 wires, right? So what do you have to do? Too many things. Let me open Pulse view. Okay, that is connected, I think. Then you have to be careful. Our I2C, right? I2C clock is what? 100 kilohertz. I2C clock, okay? That clock is SCL. That is that clock. That is 100 kilohertz. Okay, that means using logic analyzer, you want to take samples, right? You want to take the samples. Take samples. Okay, then display that that the sampled data onto your computer screen, right? So the question is how frequent, how fast that sampling, this sampling clock frequency should be. Sampling frequency. For sure, that should be supposed to be, much faster than this number. At least twice faster. Okay, but here, let me use 20 kilohertz. How about 1 megahertz or 2 megahertz? That range. 1 megahertz means 10 times faster. Okay? 10 times. So 2 megahertz, 20 times faster. Okay, 2 megahertz. And how many samples? 2 megahertz, 1 mega samples. That means what? 0.5 second words data. So if you change it to 2 mega samples, then 1 second words data, right? So let me change it to 20 mega samples, then 10 seconds words data, right? So let me run it. Let me set like this. Then, one good thing about this pulse view is, check out this. This pulse view understand I2C protocol. I2C protocol. Look at this. Embedded. Then look at this. I2C. Okay. So, let me remove this. Delete. Then double click this. Then I2C that appears. And here you can set. Okay, we connected two wires, right? SCL and SDA. And it is you can set which one is SCL, which one is SDA. D0 is clock and D1 is data. You can set it. Okay, so we can set it later after collecting data, because we don't know for sure which one is clock, which one is data. Okay, so now let's run. I did everything correct, right? Press F8. Press F8. What is going on? What's going on? Okay, let me download it. I don't know what I did. Okay, start here. Then let me press F8. Okay, now it's working. Then it is keep printing out that message, right? That temperature, you are reading a high register and low register from motion sensor. Okay, so let me run now. Run. Is it? Okay, some went wrong. Okay, let me do this. Scanning 2 megahertz, then probably 20 million samples. Then okay, I think it collected everything. 20 seconds words data. Manipulate full screen. Okay, you see some, something. You see something is going on. Okay, let me zoom in. Zoom in this part. this. So I2C communicate. Okay. I2C communication is going on between two wires. So by looking at this pattern, this waveform, I think D1 is clock, D0 is data, right? So start condition, right? It goes down while clock is high. Let me do this for here, add embedded and I2C. Then assign pin. Okay, clock is D1, right? And data D0. So it is converting. So the first view is converting that ones and zeros to human readable form of the protocol, right? So compare that against what? Against, because we are reading from temperature register. Okay, so compare that. See, okay, here. Start condition, right? Start condition, don't worry too much about here. Address 18. You are writing, right? So look at this one. Slave address and write. So here, slave address write. So write, right? W, 0 is write, right? And then slave is acknowledging, ek. Then sub address, register number. So here, 0C. What is 0C? I think, what is 0C? According to the spec. Zero C, right? Zero C is temp L, low temperature, and high temperature 0D, 0C. Right? So it is reading from 0C. So you are writing 0C to motion sensor, right? So we are here, right? Self address, then repeated start, right? 18. Device a motion sensor ID. Then, so you are reading data read 00. Okay, so with this full chunk. Okay, 1, 2, 3, 4, 4 chunk of detailed operation. You are reading just one, one register. Let me open the row register. Then you are supposed to read high register, right? Check on this. Where's that? Okay, here. Okay, here. 0D now, right? High register 0D. High register number. Then the value is FB. So because I think because of this, high spec, right? High spec, negative number, right? Spec works really good. Okay, that's what I prepared for today. Any question?
교수님 그럼 저 데이터 읽는데 클락을 몇 번이나 쓰는 건가요?
굉장히 많이 쓰네, 그렇지? 그거는 네. 여러분이 이 코드를 여기 슬립이 있긴 하네. 슬립이 있어도 사실 요거를 하는데 하이와 로우를 읽는 걸 볼까 한번. 지금 여기 하이였지? 0D니까. 그 다음이 로인데 인터벌이 꽤 실제 리얼타임으로 봤을 때는 인터벌이 꽤 있는 거지. 이렇게 되는 거네. 시간은 여러분이 좀 여기 있네. 따져보면 좋을 것 같고 여기서 하이를 읽고 그 다음에 로우를 읽는데 시간 인터벌 3.6 이게 리얼타임인지 모르겠네. 실제 3.6초 3.7초 하지만 이 웨이브 폼으로 봤을 때는 굉장히 뭐 길어 보이지만 0.1초 상관이에요. 이게 0.1초 대략 0.1초. 이 코드를 수행할 때 이 코드 이게 API이기 때문에 이것도 컴파일러로에 의해서 여러 가지 명령어들로 이제 트랜슬레이션이 되잖아. 그렇지? 그리고 얘한테 쓰고 결국 API가 결국은 얘한테 쓰고 그거에 의해서 트랜잭션이 발생하고 그 시간이 이제 꽤 이제 걸리는 거죠.
저희 이거 할 때는 API 사용하는 건가요?
뭐라고 다시 잘 안 들리네.
그 예전에는 그 프롬 스크래치로 과제 계속 했었는데 ISQL에는 API가
이거는 좀 복잡해서 레지스터를 직접 건드리는 게 좀 복잡해서 그리고 내가 다행히 요 레퍼런스 코드를 찾았어. 요 API를 구현한. 내가 레지스터를 건드려서 어셈블리로 해보려고 했으나 조금 여의치가 않아서 다행히 이걸 하여튼 찾아갖고 이걸 여러분들이 사용하면 될 것 같아. 그리고 요 ISQC 컨트롤러의 어떤 부분을 건드려야 되는지는 쟤를 따라가 보면 알 수가 있는 거지 사실은. 이 코드, 이 함수를 따라가 보면 컨트롤 레지스터 건드리고 있구나. 어드레스 레지스터, 데이터 레지스터 건드리고 있구나. 그걸 우리가 파악할 수가 있잖아. 여기 따라가 보면. 그렇게 그 방식을 좀 취하는 게 좋을 것 같아. 클래스에서는 지금. 인더스트리에서는 좀 옵티마이즈된 코드를 짜려면 글쎄 뭐 어셈블리로 해도 좋겠지만 지금 여기서는 이걸 그냥 여러분들이 사용하면 될 것 같아. 오케이. One announcement before closing up. We have midterm exam on 27th. 2 weeks from today. Okay, so midterm exam. And no class on 25th on Monday. So we have two classes before midterm exam. And midterm exam is you have to come to the classroom. You should come to the classroom for midterm exam. This is not online exam. Okay, please come to the classroom. All right. Anything you want to ask? Okay, I'll see you next time. Bye. Okay, thanks.